Hi everybody, welcome to lecture 19b on leaving groups. Before we get started, just a few announcements. First of all, I'd like you to notice that I missed you guys in class, so I decided to add all of you over there. You can pick out whichever mole you are, but there's my little class right there, because it's really no fun giving a lecture to nobody. So I have all these little moles, you see those, but I have all the other ones set up so that I can do my lecture to them. And pretty soon I'll start naming them after you guys. So take your favorite color. Who would you be? Other announcements. You can see on this screen I have some websites and a PDF link. This PDF link is in our Sakai site in the resources section. These are all places that you can go to get more information about the content that we're doing. Since we're going to be virtual anyway, you might as well go look at the other websites that I think are really helpful in explaining some of the material we're talking about. All right, let's get busy on leaving groups today, because let's, do a little wag to get our organic land reactions going. And these tosylates and mesocylates that I've shown you on the screen, these are going to become leaving groups very soon. And very important leaving groups. So I thought I'd just start out by putting them way out there. They're really ugly and messy. We'll come back to them in just a second. Okay? So when it comes to a leaving group on a nucleophilic substitution reaction, what's the best leaving group you could possibly have that wants to just fall off your organic molecule? And here's the #1 premise for that. The best leaving group is a stable, weak base, something that doesn't react. So if it doesn't react, it's weak, sounds like something that would be great to have it fall off your molecule and not come back on. So let's revisit some of the weak bases we've seen so far, and these shouldn't be surprises. So notice we have our halides here. These are all very stable weak bases, along with our water. And notice the water comes off of our protonated molecule. You can't have water on it to start with. Curious where that little guy comes from. We'll come back to that in a second. So these would be all really good leaving groups, as well as our mesylate and tosylate. And I want to show you why these would be really good leaving groups. You might have already spied it. But when you look at these negatively charged oxygens, this negative charge no longer has to sit, again, just on that oxygen. It could resonate. And it could resonate to the other oxygen. And so there's a high degree of resonance stabilization here for this negatively charged oxygen, which makes this a very weak base. It's not eager to grab a proton and act basic. It doesn't mind being negative. I can spread it out amongst 3 different oxygens. So negative charge is stabilized. The other beauty of this, now that you've seen its ugly structure, is that now we can start abbreviating tosylate with OTS, negative OTS, and negative OMS. So you might see it in that coming up in a minute. This is to help us abbreviate this big, huge, resonance stabilized, negatively charged tosylate or mesylate. What makes for really lousy leaving groups? Really strong bases. Ones that really want to react fast and hard and don't want to, be out there negatively charged all by themselves. So poster children for this. OH- is an awful leaving group because it's a strong base. And so you can see all these other ones like H- are also very, very ugly. Don't want to go there. So this is why when we have an alcohol like ROH, we actually make it into a better leaving group by adding H+ to it. Okay, and that's how we get it to fall off as water. All right, so now that's basically it for leaving groups. Okay, but I'd like to also show you why mesylates and tosylates are even introduced here. They're such scary looking little structures. Why would I torment you with these in the virtual Orgoland and cyberspace world? Well, let me show you why. What if I want to start with this alcohol, right? And this is a chiral alcohol. And I want to do an SN2 reaction on this alcohol to create this ester, okay? And this ester, you can see, has gone through inversion from a backside attack. So for a nucleophile, I guess I would need the negatively charged form of this ester. So up pops potassium acetate, and I put it in acetone because, remember, that is an aprotic solvent. So that would even favor my SN2 reaction. But most importantly, potassium acetate dissolves in acetone. So I get my acetate and an aprotic good solvent for SN2. It's ready to do a backside attack. But wait, OH is a lousy leaving group. So what we normally would do is at this point we'd throw in a little H+, and this would supposedly protonate our OH and allow for a reaction to occur. But what actually happens, oops, sorry about that, is this does not happen. This reaction does not form this product. Wah, wah, wah. I had a sound effect in here, but it just, I don't know, something about Zoom doesn't like my little sound effects, and so I had to take it out. So I'll have to make up my own. Wah, wah, wah. No reaction takes place. Why? Everything seemed to be so set up perfectly for an SN2 reaction. The problem? I had an acid-base reaction take place first. I added acid and I thought it would protonate my OH. But you know what? Here's a negatively charged oxygen. It's going to protonate this species, is going to grab this H+ and fall in love with it and form beautiful acetate product that's known as acetic acid, aka the main piece ingredient in vinegar. So if you want to make vinegar, this is great. But if you want to make this acetate, the octane 2L acetate, won't happen. So I need to find a way to take my alcohol and turn it into a good leaving group so that I don't have to use acid. Because we're going to be playing around with a lot of alcohols and want them to be good leaving groups. But maybe I don't want to throw them in a bunch of acid that would protonate my good, strong nucleophile. So guess what? Yep, you saw it earlier. Tosylates and mesylates to the rescue. I had another sound effect in here. It was like, woohoo, yeah, cool, yeah, woohoo. But Zoom didn't like that either. So maybe in the future we'll figure out a way to make it work. So if we do the mesylate and tosylate, this is how that mechanism works. Now, feel free to stop this video at any time and repeat this piece. Go slow, go fast. Skip over any parts of the video. That's the best part. You know, it's like having the remote control. Wish you had that in lecture too. Whoop, go faster, Nick. Whoop, go slower, Nick. Now you can. Okay? So this is the key to making alcohols a really good leaving group. Before I want to turn it into the acetate and do the reaction, what I'm going to do is let my alcohol act as a nucleophile. Yep, it has a lone pair, and I can have it act as a nucleophile on my tosyl chloride. It can react, and this sulfur is very partially positive because it's got this partially negative chloride on it. Okay, and so it's going to react and form this molecule here. Now the H is not falling off. It's very important that you don't just have this H fall off willy-nilly whenever you want to, because alcohols are not acidic. So what happens is the alcohol acts as a nucleophile on the tosyl chloride, and then it says it's sitting in pyridine. What's pyridine for? Pyridine is awesome at this point because it is an organic base that can come up and help abstract that proton and give the oxygen its lone pair back to create this tosylated product. And now it has all of its lone pairs. And I have a tosylate. I could have done this with the mesyl chloride as well. I'm just showing you here with tosyl chloride. Okay? And the beauty of this is I've taken my alcohol and made it into a mesylate or a tosylate. This one is a tosylate. And now I have a great leaving group. Do I need acid? No. So now I can do my SN2 reaction with my strong nucleophile, my acetate ion, and acetone, and no acid is present. Woohoo! That is awesome. And so then I can do my inversion, and now the whole mesylate, as you can see, and the whole tosylate, this whole piece acts as the leaving group. This whole piece acts as the leaving group. When this does a backside attack on this carbon and kicks off that oxygen and leaving it negatively charged. Is that a problem? No, because it's got all that resonance. So this is the best way I can do an SN2 reaction on an alcohol without using acid, because acids want to protonate my charged nucleophiles. Oh, don't do it. It's bad. Okay? Cool. Can alcohols do anything else? This is the end of my talk, my video here, and I'd like to kick it your way to see if you can figure out which one of these products is formed from this two-step reaction. And the reason you can tell it's two steps is, just so you know, this is kind of new. We'll always write number one. This actually is one whole reaction. It produces a product, not some intermediate transition state. Nope. Reaction one produces a compound that I can physically isolate in lab. Remember lab? Remember lab? I wish we were in lab. But I can physically isolate the tosylated chloride, the tosylated alcohol. And then I can do step two, which chances are it's an SN2 reaction. Just maybe. Okay? So I hope to see you soon, Monday night, or in our Monday night Zoom meeting, or in our class on Tuesday morning. Okay? Have a great time. I hope you're all well and safe and healthy. Bye.